Hello friends, in this video we are going to discuss about the critical wavelength of the semiconductor. As we know that if we have a semiconductor, let us assume that we have a semiconductor and this semiconductor has a band gap of Eg, that is the band gap energy of the semiconductor. Now, if we take a diagram of a semiconductor, suppose this is the semiconductor and this is the bulk material. In this semiconductor, let us assume that some incident light is there. That means some amount of light that is incidenting on this semiconductor, and the light consists of photon particles which have energy of h nu each. And let us also assume that is the wavelength of the light is lambda. For this, we can write that according to the wave particle duality, we can say that light wave can be thought as stream of photon particles. And these photon particles, that is each photon particles will have an energy E equals to h nu, where nu is the frequency of the light. Now these photon particles will be absorbed by this semiconductor. So the photon particles energy will also be absorbed inside the semiconductor. So now if the energy of the photon is greater than or equals to the band gap of the semiconductor, that is Eg, then we can write that E photon means h into nu, that will be greater than or equals to the band gap of Eg. And if we substitute mu equals to c by lambda, where c is the speed of the light and lambda is the wavelength of the light. If we substitute that, then we get h by lambda, where h is the Planck's constant. Now, if we put the value of h and c, that is putting the value of h and c, we can say that lambda will be less than equals to h into c divided by Eg. So let us put the value of h and c. So h has a value of 6.6 into 10 to the power minus 34, and c has a value of 3 into 10 to the power 8, and this h value will be in the joule, so we have to convert it in the electron volt. For that we have to divide with 1.6 into 10 to the power minus 19, that is the electronic charge, and here it will come as 10 to the power 6, and this Eg. So lambda will come as 1.2376 divided by Eg, and this Eg will be in electron volt. This is in electron volt. So finally we can say that lambda will be less than or equals to 1.237 of Eg. So this is the range of lambda. Now from this range we can see that the lambda will have a maximum value. So lambda max can be written as 1.37 divided by Eg in electron volt, and lambda will be in micrometer. So this is the value of lambda in micrometers, and this lambda is also in micrometer. So this is the maximum wavelength of light that will be absorbed by the semiconductor. Not all the wavelengths of light can be absorbed, only this range of wavelength will be absorbed by the semiconductor, and this is called the critical wavelength. So we can say the maximum wavelength lambda that will be absorbed, that will be absorbed by the semiconductor called critical wavelength. This is a very important parameter of the semiconductor, that is the critical wavelength. So we can write that lambda critical for any semiconductor in micrometer will be equals to 1.37 divided by Eg in electron volt, or we can say in approximately we can say 1.24 divided by Eg in electron volt. This is the equation of the critical wavelength of any semiconductor, and this critical wavelength depends on the Eg. As Eg of the semiconductor, that is the band gap of the semiconductor, if increases, then we can say that lambda critical will be decreased, and this is an important parameter for every semiconductor. Since the Eg determines the lambda critical, so we can say that every semiconductor will have different lambda critical, because the band gap of different semiconductors will be different. That's why the critical wavelength will be different. So this is all about the critical wavelength semiconductor. Thank you.